Okay, in this video we're going to start talking about logarithms, but before we do that, let's review our exponent rules, okay? So exponent rules. So let's say let S, T, A, and B be real numbers. And then A and B are greater than 0. That means they're positive, okay? So if I have some number A raised to the S power times that number A raised to the T power, it's the same thing as A raised to the S plus T. Okay, so we add the exponents when our bases are the same. Our exponents S and T, the base has to be the same. Multiplication, here we rewrite it as addition in the exponents. Let's say I had A raised to the S power, in parentheses, raised to the T power. Okay, so I have a base raised to a power, raised to a power. That's going to be the same thing as A, the base, raised to S times T. Okay, so when you have a base with a power raised to another power, we can rewrite those powers as multiplication. Suppose I have two numbers, A and B, raised to the S power. Here, I would apply my exponent to both of these numbers. So that's the same thing as A to the S times B to the S. Okay. Also, 1 raised to a power, let's say S, is always going to equal 1. 1 times itself, however many times, is always going to be 1. If I have some number A raised to the 0 power, that's always going to equal 1 by definition, okay? And let's say I have A raised to a negative exponent. Remember, a negative exponent means this whole thing is really in the denominator of a fraction, so that's the same thing as 1 over A to the S. I could also rewrite that as 1 over A raised to the S power in parentheses. Okay? And it's still going to equal this here because if I applied my exponent to both my numerator and denominator, which is what this is telling me I could do, I have 1 to the S over A to the S, and 1 to the S we already know is 1 over A to the S. Okay? So here's a couple of different ways this could be written. Now, when we talk about logarithms, it's really important for you to understand that we're talking about exponents. Okay, negative exponents change everything to fractions, 0 exponents change everything to 1. But let's say we have A raised to the power of y, and that is going to equal x. Okay, so A here is our base, y here is our exponent, x is the value that we would get if we were able to evaluate this. So 2 to the third power is equal to 8. 2 is our base, 3 is our exponent, and x is our value. Okay. So logarithms give us a way to rewrite exponents. So if I have a to the y equals x, I want to be able to rewrite this with a logarithm. Okay, so that means y equals log base a of x. Okay, so a here is still our base. Y here is our exponent. X here, our value, is something that we call the argument of the log. Okay, but from over here, remember, that's the result that we're wanting to get if I had taken a and raised it to some power. Okay, so the value is what we call the argument of the log. Something I want to point out right now before we continue is that log by itself means absolutely nothing. You have to have an argument. Okay? Here, I don't see a base written on my logarithm. It's empty. Over here, I had log base a. Here, I don't have anything. And if you don't see a number as the base of the log, we automatically assume it to be 10. So that would be the same thing as log base 10 with k as our argument. Also, if you have log base e, this is a special logarithm. This one is also programmed into your calculator, except we call this the natural log. And we write it as ln. Okay, so log base e of k, you would more likely see it written as ln of k. When you see the natural log, you should not see a base written here. It is already base e. So this gives us a way to rewrite exponents. So let's do that. So let's say I have 1.2 to the fourth power, and that's equal to some number k. I could certainly take 1.2 and put it into my calculator with a power of 4 to see what it equals to, but we want to rewrite this as a logarithmic statement. So 1.2 here is my base, so I need to write that as log base 1.2. My result is the argument of the log, so that would go here next to the logarithm, k. And remember, my exponent is what this all equals to. So that we can say is 4. So the point of this is we're going to start solving equations with our variables as exponents. And this will give us a way to do that. Okay? If I have e to the x equals 9, here my variable is my exponent and it's unknown. E is the natural number e. This is what we use natural log for. So if I wanted to rewrite this as a logarithmic statement, I have the natural log. I don't need to write e here for my base. We already know it's there. 9 is the argument of my logarithm, the value it's going to end up equaling. And then my exponent here is what I set this equal to. Okay? If I have a logarithm, I can rewrite it as an exponential statement. So let's say I have log base a of 4 equals 5. Now remember, log base a means a is my base. What this is all equal to, the number 5, this is my exponent. And the argument of the log is the result that I wanted. Okay? So this is why I keep saying logarithms are exponents. Okay? A to the 5th power equal to 4 is the same thing as log base a of 4, which is equal to 5. Okay? It gives us a way to solve for exponents. If I have ln of 5 equals x, or the natural log of 5 equals x, okay, remember, the natural log is base e, so I would rewrite e. Okay, what it's all equal to is x, and then my argument of the log is 5. That's my result that I wanted. Okay, so we can go back and forth. If you have your calculator, I know mine is really hard to see. Yours may not look exactly like that, but somewhere on there, you should have a logarithm button, a natural log, and an e exponent, and a 10 with an exponent. Okay, you may not have the 10 with the exponent, because you can certainly just type in 10 and raise it to a power, but you should have some way of evaluating e. Remember, e is like pi. It's an irrational number that we know. So you don't want to go into the section not knowing where these things are. Now, having just said that, we said e is an irrational number that we know. X is my exponent, and then I can evaluate the natural log of 5. I could figure out what exponent I can put on e to make it 5, and that would be the natural log of 5. Okay, so natural log of 5. This is another reason that we like logarithms, because we can work with them without having to change everything into these long decimal numbers, because this is a repeating number. This is a fraction that keeps on going. You don't really want to round those off there. Okay. So what if we're given something like log base 2 of 16, and we're asked to evaluate or solve? Okay, remember, this is an exponent, and the way you can think about this is 2 raised to what power is equal to 16? Okay, that's what we don't know. So this reads as 2 raised to what power equals 16. Okay, so I could convert this to an exponential statement. 2 raised to some power, we'll call it y here, is equal to 16. I know that I can rewrite 16 as 2 to some power. Okay, so I've got 2y equals 2 to the 4th power is equal to 16. And once I'm here, once I have rewritten 16 as the base 2 with the power of 4, after that, I'm really only concerned about the exponents. So that tells me y is equal to 4. And if you take 2 and raise it to the 4th power, that does give you 16. Okay? So it's a way to ask this question. We don't want to forget that we could also have fractions here. What if we said log base 3 of 1 over 9? Okay, so this is asking me 3 raised to what power is equal to 1/9? So 3 raised to what power equals 1 over 9? Okay, so that's what we want to know. We want to know the exponent we can put on 3 that is going to result in 1/9. So 3 raised to some power is equal to 1 over 9. Now, on this one, I know that I can rewrite 9 as 3 to a power. So let's say 3y is equal to 1 over 3 squared, because we know 3 squared is 9. And remember, if I change the sign of the 2, my exponent, I can rewrite this not being in a fraction. Okay, so that is equal to 3 to the negative 2 power. And now that I have the same base, I can just work with the exponents. So here y equals negative 2. Okay, that means the log base 3 of 1/9 is equal to negative 2. So I want to make a note here. I'm going to write it so I say it slowly. Note, our result our exponent can be negative. However, the argument of a logarithm can never be negative. So if I put in my calculator that natural log with negative 2 as my argument, it's going to give me a domain error because it doesn't make any sense. Okay, our arguments have to be positive numbers. Also, the argument of a log can never be 0. So if I have log base 10 of 0, I also get a domain error. You can't put an exponent on a number, on a positive number, that is going to make it 0. Remember, our bases had to be greater than 0. So you'll never be able to put an exponent on there that is going to make it 0. So let's say I wanted to solve a logarithmic equation. So let's say I have, I don't want to write in red, log base 3 of 4x minus 7 equals to 2. Now I have the logarithm equal to some number. I don't have anything multiplied in front of the logarithm. I don't have anything being added or subtracted to the logarithm. And when I have it in this form, I can convert it back to an exponential statement. Remember, this says 3 is my base, 2 is my exponent, and this is what it's all going to be equal to. So I could rewrite this as 3 squared equals 4x minus 7. And now I can solve this. 3 squared is 9. That is equal to 4x minus 7. Okay, then I would add 7 to both sides. So I have 16 equals 4x. Here I would divide both sides by 4. So I have x equals 16 over 4. 16 divided by 4 is 4. Okay, and we can check this. So check. Log base 3 of 4. We found x to equal 4. So 4 times 4 minus 7. And the question is that equal to 2? So we know 4 times 4 is 16. So this is the same thing as log base 3 of 16 minus 7. We want to see if that is equal to 2. 16 minus 7 is 9. So we have log base 3 of 9 equal to 2. And we're still checking this, so I can rewrite this as an exponent to see if it makes sense. 3 is my base, 2 is my exponent, and I want to know, is that equal to 9? And it is. 3 squared does equal 9. So we know we got all of our steps correctly. Let's look at another one. Let's say I have e to the 3x equals 5. Okay, so I don't have a logarithmic equation here. I have an exponential equation. My variable's an exponent. But I have this without a coefficient, without anything being added or subtracted to it, and it's equal to a number. So I can rewrite it as a logarithm. Okay, so my base is e, and when my base is e, we have the natural log. Okay, I don't have to write the e. Our result here is our argument, 5, and we set it equal to what our exponent is. Okay, now to solve for x, I would divide both sides by 3. So x equals the natural log of 5 divided by 3. Okay, you're taking the entire natural log of 5 and dividing it by 3. So do not think that this means a natural log of 5/3, because it doesn't. Okay, you want to treat this natural log as a number by itself, and you can certainly divide a number by itself. You don't want to take something outside of it and include it into the argument of the log. Okay, and this itself is an answer. We know that we have the natural log button in our calculator, so this is what we call an exact solution, because it includes all of those decimals. Now, if you wanted an approximate answer, we would just stick it into a calculator. We don't have an easier way. Well, there are ways to figure out what it is, but we don't want to have to learn those or deal with them on a test. So I have a fraction button. I have a natural log button here, natural log of 5. Make sure I close my parentheses. I can go down, type 3, so I can input exactly what I see into the calculator. If I hit enter, it's going to give me a decimal approximation. So let's call this 0.5365 if I want to round off to 4 decimals. Okay. Now, as you start doing these equations, I want to make a note that the only ones you can evaluate in a calculator are log base 10. Okay. And remember, if it's base 10, we don't write the base on there. We just write log. Or the natural log. Okay, those are programmed into your calculator already. If I wanted to evaluate log base 3 of 2, I would have to do something else, and that's not in this section. So we'll come to it in the next one. Okay, so this is not done in a calculator directly. I want to do a couple of more quick examples with something that looks really messy. So let's say I have 3 times e raised to 2x plus 1 minus 2, that is equal to 10. And I want to solve for x. The important thing for you to note here is that this, as my exponent, 2x plus 1, is only applied to e, okay? 3 and e are not in parentheses together raised to this power, so 3 has nothing to do with this exponent, okay? This negative 2 here has nothing to do with this exponent, okay? But before I can really work with this, what I don't have is just a number with an exponent equal to some number. So let's use algebra to move stuff away. I can add 2 to both sides to clear this 2. So that would give me 3e to the 2x plus 1 equals 12. And then I want to get rid of this 3, and I can do that with division on both sides. So 12 divided by 3 is 4. So I have e to the 2x plus 1 equals 4. Now I have a number with an exponent equal to some number. I can use a logarithm to continue solving this. Okay, I have e here, so I want to use the natural log. So the natural log, remember what it's equal to is my argument. So the natural log of 4 is equal to 2x plus 1. And remember, the natural log of 4 is a number all by itself. So I'm going to treat it like a number all by itself. To solve for x, I want to subtract 1 from both sides. So I have the natural log of 4 minus 1, and that is equal to 2x. And then to get rid of this 2, I divide both sides by 2. So I have x equals the natural log of 4 minus 1, all divided by 2. Okay, I have solved for x. This is my exact solution. Okay, if I needed a decimal approximation, I would get my calculator, and I can do this because it's natural log. Okay, so I have a fraction button. I have my natural log. I can type in 4 as my argument, and here it is essential that you close those parentheses. Okay, minus 1. Now I can use my down arrow button to get 2. hitting enter, that gives me a decimal. So approximately 0.1931 if I wanted 4 decimals, or however many it says to round off to. Let's look at one more like that. This will be my last one for this section. So let's say I've been given 4 times 10 to the 2x plus 1 equals 21. Again, my 4 here is outside of those parentheses, so my 2x here as my exponent doesn't have anything to do with this 4. It doesn't have anything to do with this 1. But I don't have the form that I want to change it into a logarithm. I don't have a number with a power equal to something else. Okay? So again, we need to use algebra to isolate this 10 to the 2x. So I can subtract 1 from both sides. That gives me 4 times 10 to the 2x equals 20. Now I want to get rid of this 4. So I can divide both sides by 4. That gives me 10 to the 2x equals 5. Now I have a base with a power equal to some number. My variable is in the exponent, so I can use a logarithm. And this is base 10 here, so rewriting this, I'd have log base 10. My argument is 5. And that is equal to the exponent of 2x. Okay? Log base 10 of 5 is its own number, so I don't have to do anything here. I just need to divide both sides by 2. That gives me x equals log base 10 of 5 all divided by 2. This is my exact solution. If I wanted a decimal approximation, get my calculator. So log base 10 of 5 divided by 2, that is approximately 0.3495 if I'm going to use 4 decimal places. And we're done. I know I skipped over the graphing, but I think what you have in your textbook right now is sufficient for graphing. Just review those rules to graph it, okay? If you want to pull up a graphing device and start graphing them that way, look at them. And you can find those patterns. I know that there's a couple of rules given in your textbook about how to graph. Really just remember that the domain is a set of positive real numbers only, okay, from 0 to infinity. The range can be anything, negative infinity to infinity. So your domain is positive, your range can be both positive and negative, okay. The x-intercept, hold on, let me write this down. Domain of a log function okay. Remember, a has to be greater than 0 and a cannot equal 1 because then everything is just 1. Okay? So domain is from 0 to infinity. Range is negative infinity to infinity. The x-intercept is 1. Okay? there is no y-intercept. Okay? Because you can't make it equal 0. You can't make an exponent, put on a number, have the whole thing equal 0. So there is no y-intercept. So the y-axis is a vertical asymptote. So if A is between 0 and 1, meaning 0 less than A less than 1, the graph is decreasing. If A is greater than 1, graph is increasing. And points. There's always points on this graph that are easy to find. Okay? 1 and 0. Why? Because anytime I stick 0 as my exponent, the result is 1. It doesn't matter what my base is. So this point will always be on your graph of a logarithm. I also always have the point a1. Okay, because if I stick 1 as an exponent on any number, it's just going to be that number. And 1 over a and negative 1. Okay, negative 1 means the negative sign as on an exponent means I'm really looking at a fraction. So if I had a to the negative 1, that's 1 over a. Okay, so you can always find these 3 points easily. What you're really looking at is it increasing, decreasing, and where is my asymptote?